until it stops working, of course. Anyway, this is probably one of the few topics that you can take out of this course and use directly in the real world, which is kind of cool. The one thing is that, it's going to be, it's common theme. It'll be years before you understand where this formula or this approach comes from, because if you were to plot these points on a graph and try to estimate what you think the line would be that best fits that data, then it's just really guess and check. You look at it and say, oh, I think that maybe that line's the best fit, all right? But the reality is that there's a calculus-based formula that makes the determination of what the line is that best fits that data set, all right? So calculus, not Algebra 1. So it'll be a while before you can actually see that. In fact, the first time I'm able to go over this concept in a way that students would be able to understand it would be in Calculus 3, right? So that's years away, so I'm not even kidding, right? So it's like college. For now, what we have is a nice approach that you can use in your graphing calculator, and it's a very easy approach to help you determine the line that best fits the data. So you're just going to follow a bunch of steps and get an answer, all right? So it's kind of a recurring theme in the course, where it's like you'll follow a bunch of steps and get an answer, and then just go from there. All right, so we looked at scatter plots to determine if there was a correlation. Sometimes the correlation was positive, meaning it was going uphill from left to right. Sometimes it was negative, if it's linear, which means it goes downhill from left to right. All right, so correlation gives you a sense of whether a line would be an appropriate way to represent the data. But then once you make the determination, oh yeah, a line would be a great way to represent this data, then your job is to actually come up with that line. All right. So our first job is to construct a scatter plot. Scatter plots are very easy to do conceptually. They're just very tedious. I mean, plotting points is not entertaining in any way, shape, or form, so well, you didn't need me to say that. The graph is already scaled for us. X against Y. It seems to be going by 2s, 2, 4, 6, 8, 10 on the base, and then also 2s on the vertical axis. You notice the little break marks there? That indicates that there's a gap between 0 and 20, right? It also means that there's a gap here, setting us up to actually start off in the neighborhood of 46 and on Y and 20 on X. All right, so we're still going to estimate, but at least we don't have to have like a whole lot of dead space going from 0 to 20 in X and 0 to 50 in Y, or 0 to 46, all right? So we're going to ballpark. So 26, fortunately, most of the X values, or at least maybe half, yeah, I'd say most is reasonable. Most of the X values are even numbers, so they're going to plot nicely. The odd numbers will just be half boxes, so that's not bad. So 2649, so I'll have to estimate the Y value. And I'm going to create a thick. So 2649 would be right about there. 2850 is going to be right smack on the, well, okay, that's not smack on it. That's not smack on it either. Still not smack. That's smack. All right. 3057, 246 ish. I think I had it. 3254. 3460. 3558. 3764. 3866, right about yeah. 4163, like right about yeah. And then 4572 would be right about yeah. Something like that. All right, so if you're a little off, nobody's losing any sleep over it. And if you're a lot off, that's a different story. But if you're just a smidge off, nobody's looking to take off credit for that. If you're ever in doubt, like serious doubt, just make your point larger so it covers a wider space. In which case you could say, well, the point's in there somewhere. Like I'm right. I mean, I'm like 1% right and 99% wrong, but I'm still at least somewhat right, so give me credit, please. All right. So that should do it for the graph. Now, just visually, it appears that there is a linear relationship, or at least not necessarily a very, very absolutely perfect linear relationship, or maybe very strong, or maybe moderate to very strong. But you can see that there's definitely an upward tick here. It's going in the upward direction. As the low temperature increases, the high temperature increases. Right, so describe the relationship between low and high temperatures. I think I just did. Right, but what they're looking for is like a common way of speaking, right? So put it in your own words. You could say that there is a positive correlation, but we really want to talk about what we know about low and high temperatures, right? So you could throw in positive correlation. I don't think I need my marker to be that thick anymore. I'm going to abbreviate just because we're taking notes, but on the regents, don't abbreviate. Just write every word out. You have enough time. On an assessment for me, like it'll be a group assessment, so you don't have to worry about it too much. You can abbreviate, but you know, like if it's not something that a reasonable person can understand what the abbreviation is, like if you wrote PC, I don't know what you mean by that. Right? Write enough that I can make a reasonable determination of what you're trying to abbreviate. On the regents, just write the whole word out.
When's the group assessment going to be?
It's going to be end of this week, beginning of next week. All right, we're pretty much there. We're getting into review, and then I'll talk more about that later. All right, so as low temperature increases, high temperature increases. I mean, I don't know. It's one of those things where I would think you would find a little bit of common sense in this, although, you know, at the old can home front, it doesn't always play out that way. So we're always in the morning trying to figure out, like, is it a jacket day? Is it shorts day? You know, like, what are we working with here? And so someone in my house who shall remain nameless will look up the weather report and see what the temperature is outside at 6 o'clock in the morning. And we'll say, it's 55 degrees out. Oh, today's a jacket day. What's the problem with that?
It'll get warmer.
It's going to get warmer. Yeah, it's at 6 o'clock in the morning. It's 55 degrees. That's in the range of the low for the day. So if it's already 55 degrees, now that person has since, you know, come around and realized that things change. And so if you're already at 55 degrees at 6 o'clock in the morning, we're looking at a pretty warm day, right? Probably in the 70s, right? So we're looking at a relationship between low and high temperature. Now, if the temperature at 6 o'clock in the morning is 15 degrees, would you expect it to get up to 75 degrees?
No.
Probably not, all right? It could be one of those weird days, those beautiful snow days where you have like a foot of snow, and then by the time 3 o'clock in the afternoon rolls around, it's like 60 degrees and it's all melted. Like, that's an anomaly. That doesn't always happen. The best snow day is when they cancel school and then it never snows. Like, that's the best one, because then your whole day is open. But second only to that is the one where it comes down, you got like a foot on the ground, and then by the time lunchtime rolls around, you didn't even have to shovel anything because it all melted, you know? All right, so the next part is to use our calculator to find the equation for the line of best fit. All right? And then we also need the correlation coefficient. Right? So correlation coefficient is the R value. We know that, but we haven't actually talked about how to get the R value. So calculators are the name of the game here. Now, I'll even tell you that sometimes you don't even have to come up with a scatter plot. Sometimes you just want to get a look at what the scatter plot will give you, in which case your calculator is the way to go there. So I'm going to do it on both. In either case, you're going to hit first the mode key. Hit the up arrow so that you're at the bottom of the screen. The default setting on your calculators for some reason is that stat diagnostics are off. I don't know why. Been using these things long enough to be able to determine like what's useful and what isn't. I can't figure out why it would be useful to have it as off as the default. So when you hit the up arrow, so again, you hit the mode key, you hit the up arrow, it brings you to the bottom of the menu where it says set clock and things like that. Go to stat diagnostic, go to the word on and hit enter. Your stat wizards, you should have that on. All right, that's just a good thing to have on. Now, for whatever reason, that's defaulted to on. I don't.
When they reset it.
When they reset it, stat diagnostics are going to get turned off. Yeah. Now, if memory serves, I think you'll have a reminder to put your stat diagnostic on, but I wouldn't plan on it. Especially if you're in an alternate location when you're taking the region. You may not have a person in there that really knows the ins and outs of the calculator. Or, worst case, eventually you get the information, but it's like an hour in, and you're already like putting the finishing touches on the test, and you're like, oh, that would have been good to know an hour ago. You know, so you never know how these things go. All right, so stat diagnostics go on. Now, if your calculator doesn't work that way, like for example, like the one on this screen, okay, well, of course, yeah, your calculators won't look like this. There's another way to turn your stat diagnostics on. You go to second catalog. Well, second 0 is catalog, and scroll down to diagnostics on. Now, if it worked that way, it shouldn't have a problem. Okay, well, this calculator is sufficiently different that it won't play out. So let me just do it on the other one. So second 0, you scroll down to diagnostic on. So when you went into the mode, if you didn't see stat diagnostic as an option, then do this. Second 0, and then go down to the D section. Find the one that says diagnostic on. It's a command. Hit enter. It brings up the command. Hit enter again, and it executes the command. All right. So that's if you have a TI-83 or a TI-84 with the older software. Now, just a note on that. If you have a TI-84 and it did not bring up the stat diagnostic, then you just need to upgrade your operating system, and you could be on the same page with everybody else. All right. But this is really for anybody who has a TI-83. All right. So, data goes in, just like it would if you were finding the mean standard deviation, except we have 2 columns of data. So stat, edit. I have information stored in L1 and L2. So I'm going to clear that out. Clear, enter, clear, enter. And then just type in my X values in L1. Now that whole stat diagnostic thing, we'll find out in a couple minutes whether people were successful in being able to turn that on, aka you were paying attention when I went over how to do it. Because we're going to execute the linear regression command. If an R value doesn't appear, your hand's going to immediately go up. I didn't get that. And then I'll say, yes. That's because your stat diagnostic is not on. And a good laugh will be had by all. Hopefully you too, because we all want to enjoy that. All right, so let me see. This should work the same way. All right, so in either case, what you're going to do is quit out of here. So second mode, you want to get a fresh home screen. All right, because you don't want to take the chance of accidentally typing the command that you're about to input into a cell. It's just annoying and you don't want to deal with it. Stat, calc. So you have a choice of option 4 or option 8. The better one to go with is option 8. Although for some reason other people go with option 4. I don't know why. Stat, option 8 is the better way to go, but since you're going to be hearing it from like everybody else on the planet that it's option 4, just do a stat calc 4. All right. Stat calc option 4. So statistically, whenever you're dealing with a linear function, in math we deal with y equals mx plus b because we talk about the slope being the most important part. But when you're dealing with a data set, the starting value is where you want to, like if you're creating a graph, you want to determine where you're starting and then go off of that. Y equals a plus bx, stat calc 8, really gets you that format. It gives you your starting value and then the change from the starting value. So it's the better way to go, but since everybody is going to tell you the other way, whether they know what they're talking about or not, we'll just do it that way. All right, so enter. Now the default is L1 and L2 for X list and Y list. All right, so if you're working on a TI-83, you actually have to type in L1 comma L2. So second 1 comma second 2. All right, if you have, you get to this list and you see something other than L1 and L2 here. So let's say it was blank, or maybe it was just L3, L4. But maybe you got this calculator secondhand from somebody else and they used it for different lists. Again, the way to get L1 is to hit second 1. The way to get L2 is hit second 2. All right. The next important thing is to actually have it store your regression equation. All right. Store regression equation. Very important. All right. What this will do is take the equation, which is not going to be pretty in most cases. Sometimes it is, but it's generally not going to be pretty. It takes it and stores it into a y equals list or a y equals field so that you can graph it without having to write it down and type it over. All right. So the way to store it in would be to hit alpha, trace, and then select y1. All right. So you're storing your regression equation into y1. All right. All right, so to store, you're hitting alpha, trace, y1. All right. Now, if you're working on a TI-83, you just have to type that in as a separate thing. So, comma. All right, we have to come up with a y1, so we put a comma, and then the y1 is not as easy to come by on the TI-83. You have to hit the variables menu. Then you have to go to the y vars, y variables, select function, and then y1. All right, so not as convenient. So on TI-83 or old TI-84, hit vars, y vars, function, y1. All right. That works on the newer 84s also, but obviously alpha trace is a little easier. All right, then go down to calculate. And watch the magic. A lot of information here. We just have to kind of parse this information and see what's relevant and what isn't. Now, what they do is they give us a model at the top. All right? So they're telling us it's in the form of y equals ax plus b. Then they tell us what a and b are. All right, so we have what we need. Round the slope, which must be the a value. All right, because that's the value in front of x. All right, normally it's y equals mx plus b. This time it's a. So the a value takes the place of slope. We're going to round that to the nearest hundredth. So 1.16. plus the b value rounded to the nearest integer, right? So that's just going to be 19. The correlation coefficient is the value of r. Nearest thousandth, all right, that's 3 decimal places. So 0.948. All right, same values, right? Good. All right, so you think about things like that, that whole storing the regression equation. What could possibly be the benefit of doing that? All right, well, we created this scatter plot by hand. Well, let's say we didn't want to, or we needed to have a sense of what the scatter plot looked like, but we didn't actually want to produce it by hand. All right, the calculator already has everything it needs to create this graph for us. We have follow-up questions here that are related to this equation. Use your linear regression equation using the equation from part C, predict the high temperature when the low temperature is 60. Right, so that would be plugging in a 60 here, but this is a pretty nice looking equation. All right, so instead of doing actual algebra, which I don't want to do, what I could do first is create the graph. All right, so it's a statistical graph, right? So let's go into stat plot, second y equals. Create the scatter plot. All right, so hit enter on plot 1. Hit enter again. The first option there, now you might have done this for, what was the last one we did, a box plot? So it might be on box plot. So hit the down arrow and hit enter on the one that looks like a scatter plot. All right.
How do you get there again?
Second y equals brings you into the stat plot. Hit enter on plot 1. Make sure it's on. Hit enter on the word on. Go down into the scatter plot, or into the type, and hit enter on the one that looks like a scatter plot. Your defaults for X list and Y list should be X list and Y list should be L1 and L2. If they're not, make them L1 and L2. Second 1, second 2. How do I get a good zoom for a stat plot? Zoom stat, yeah. Zoom, scroll down to the one that says zoom stat, and then hit enter. All right, so not only did it produce the scatter plot that we had to draw out on paper, it also plotted the line of best fit. The reason it did that is because we took that extra step to store the equation in Y1. When I hit Y1, that whole equation in its full glory is stored in there. So I have everything I need. Second y equals, so hit enter on plot 1, hit enter on, hit enter on the scatter plot, make sure it says L1 and L2. Then hit zoom, and then scroll down to the one that says zoom stat, which is option 9. All right, so think about a question on the Regents where they ask you to do all this stuff, but they don't actually ask you to create the graph. Like, this is a pretty useful feature. You don't have to do any of this stuff, which is the tedious stuff. You have burned through this question very quickly. All right. So now I want to find the y value when x is equal to 60. So what is y when x equals 60? Now, notation-wise, that's saying what's y of 60. I could just type it in, 1.16 times 60 plus 19. Or, a better way to do it, I didn't even create the graph here. There's no scatter plot on the other graph. Another way to do it would be now to go to the table and get up to 60. Now, I don't want to scroll. What's another way that I can get to 60 without scrolling? You could do ask. All right, whatever you decide to do, it's in a table set, right? So second window. You can make it ask. go back into the table and just type in your 60. So 88.83. Did they tell us that around here? All right, that's one way to do it. Then just remember to turn it back to auto, right? So second window, make it say auto instead, so that you get the whole shebang rather than just the 60. All right, another way to do it is to use alpha trace. This is I think this is the better way to do it, because then you don't have to mess with any settings. If you select Y1 and then just type in your 60. I wrote Y of 60. Right? Y evaluated when X is 60. That's what I'm writing in my calculator. The calculator understands that notation, so it'll give me the same value. All right? The only thing that you might run into is a little bit of error when it comes to rounding. Like if you actually just plugged, oh, it's 19. You get 88.6 if you plug it into the formula. All right? This is actually a more exact value.
Will we get it wrong?
No, either way is fine.
Okay.
So 88.6 degrees Fahrenheit. That's if you use the formula. And this is if you use the graphing calculator TI. Looks weird. All right. So F and G are asking us to make interpretations. Explain what the y-intercept of the model represents in terms of the low and high temperatures that are being modeled in this problem. Now, the y-intercept would happen when x is equal to what? 0, right? So what that's telling us is if the low temperature, because that's x, is equal to 0 degrees Fahrenheit, the high would be equal to 19 degrees. Now, linear regression is really just talking about fitting a mathematical function to a set of data. Now, it doesn't always work out that you're going to get a value or an answer that makes sense for all cases. Right? At some point, you're looking at a value that may not fit in a particular domain, or it may not make sense in the context of a problem, or I'm sorry, I'm just getting distracted. It's weird. Like, it's just so strange. I'll get over it though. Hey, talking a mile a minute while I'm trying to explain something. Right? How would you interpret? I completely lost my train of thought. How would you interpret the slope of this model in terms of how the low and high temperatures change with respect to each other? All right. So that's a really important piece, but it also is kind of a little tough to wrap your mind around. All right. So the slope. What is the slope telling us?
Change the y and change the x.
Well, yeah. Cool.
The difference between the high and low temperature?
I think Lucy knows. One person talking a mile a minute, another person texting a mile a minute. I'm sorry, somebody had an answer. Average rate of change, definitely, but we want to incorporate the actual variables. All right, rate of change of what to what?
High temperature.
High to low. Okay, so we're getting there. All right, so if our slope is, and I'll start the sentence off. The slope was 1.16. All right, so I'll start the sentence off. There is a change of 1.16 degrees Fahrenheit in high temperature for, let's see if you can get the rest of it. For each change, each 1 degree change, in low temperature. All right. Or you could even say, for every 1 degree change in low temperature, you have a corresponding 1.16 degree change in high temperature. All right. So high temperature is outpacing low temperature, not by a whole heck of a lot, but in a predictable sort of way. Right. So if that's the case, then you know that you're using the low temperature as a predictor of high temperature. All right. So when we say something like in the last part, if the low temperature is 0 degrees, the high temperature is 19 degrees, that starts to make sense. All right. If 6 o'clock and 5 o'clock in the morning, it was 0 degrees out. All right. So 32 degrees below freezing. All right. Then at noon, 1 o'clock, whatever, if they said that the temperature was 19 degrees Fahrenheit, I don't think you're shocked by that. All right. That's because of that relationship. Now, well, actually, that's because there is a relationship. But if I were to increase this to, let's say, 30 degrees, and then increase that by 30 degrees, now you're saying, okay, well, maybe not. I don't know. Because this goes to 30, that goes to 49. That seems like it might be a little low. All right, but maybe not. All right. Because this is 1.16, and when I say that this may be a little low, the 49, I'm not saying it's low as in it should be 70. It's low as in it maybe it should be like 52 or 51 degrees, right? So this value here gives us a sense of what the relationship between corresponding low temperatures and their resulting high temperatures would be, all right? So pretty interesting stuff, and also, you know, a little mind-bending when it comes down to the slope. I think the y-intercept is a little easier to grapple with, because it really is just a matter of plugging in a 0 for x, see what you get for y, and then just try to determine, okay, well, what is this y value? And if you want to make a determination of what that y value is, you only really need to look at the label of the y-axis, all right? For slope, it's a different story. You're looking at the ratio of the y-axis to the x-axis. For 1 unit of change in the x-axis, right? What's going on with the y-axis? That's the important thing there.